Hello, Vance. Welcome
Oh,
to my show. I want to introduce Vance Holliday for everybody here. He is a professor emeritus in the School of Anthropology in the Department of Geoscience at the University of Arizona. You have done a lot of interesting work. You're specializing in human prehistory, climate change, geoarchaeology, and there's been a debate that's been raging online with respect to past climate changes around the world. And I wanted to bring you on to talk about it. And before we kind of get into the questions surrounding past climate change, I want to make sure that we're on board on the same, we have the same, what's the word I want to say? We are on the same page with respect to this past climate change. So Younger Dryas is what I want to talk about. And it's marked, Vance, would you agree that the Younger Dryas is a cold period that happened about 12,900 years ago to about 11,700 years ago, or so years before present?
the timing. Yeah, I think
The timing.
the term is a time term.
Okay.
The problem with, and the reason for that is because the climate varied. It wasn't cold everywhere by any stretch.
Got it.
There was definitely cooling at higher latitudes and higher altitudes, but even that, not everywhere. But there were places that did, particularly Greenland, northeastern North America, and northwestern Europe. But even in the eastern U.S., there were some papers. I think we mentioned them in the paper that you're going to talk about. There wasn't a dramatic change, but there were changes in a lot of places. But it's the magnitude and direction of the change.
Okay.
Very.
Okay. So the Younger Dryas, it was variable across the world. And, but you agree the timing roughly happened between 12,900 years BP, or years before present being defined as 1950 AD, to about 11,700 years before present. And so this period, this Younger Dryas, came at like a volatile part of Earth's recent history in this transition from the last glacial maximum near the end of the Pleistocene. So ice sheets are covering much of the northern hemisphere. Alpine glaciers are expanded across the world. Then there's this kind of dramatic cooling at the end of the last glacial maximum around 18,000 years ago, 20. And we kind of rapidly, or over a few thousand years, transitioned into more interglacial conditions, what we call the Holocene epoch. During that transition from that cold to that interglacial, it's pretty well understood that it was like variable climate change events, sometimes rapid, sometimes less rapid, during that transition from the last glacial maximum to the Holocene. And there could be a number of reasons those driving those factors: orbital changes, Milankovitch, internal ocean circulation changes, and so on and so forth. But the Younger Dryas has kind of stood out as being, at least in the northern hemisphere, a relatively rapid or higher magnitude climate change event, right? Would you say, of that transition to the Holocene period?
Yeah, you have the last glacial maximum, and that starts to wane about, say, 20,000, and then things start warming up, and then all of a sudden there's a reversal at 12,900, where you get cold again. So it's like the last gas of the last ice age, so to speak.
Okay,
You have this, all of a sudden you have a return to cooler conditions. Now, often misconstrued as a return to full glacial conditions. That isn't even remotely the case, but there was a change. And so it was fairly recently discovered, I guess, recent, 20 years ago, I guess, is when people begin to realize that there was a fairly dramatic shift. You could see it in ice cores and all that. So
right.
Attention, yeah.
And one of the best records of this Younger Dryas event does come from the Greenland ice core, right?
Exactly.
Yeah. And that was when it was kind of more widely recognized about, like you said, 20 years ago.
The
abruptness of it
really
was
got people's attention, like within a generation. And that's what got people people's attention, raised a lot of eyebrows. Is wow, that could happen. If it could happen then, could it happen again? So that's what generated a lot of discussion, a lot of research on the Younger Dryas.
And I liked how you brought up that term. That's a good one. The cold reversal. The Younger Dryas is almost like a reversal. It was warming. We were rapidly cooled again. And
Right.
so, in places, and the Greenland showed that transition, that reversal was relatively rapid. And for those that don't know, Younger Dryas is named after a plant, the Younger Dryas flower, and the pollen from that flower was found in sediment records across Western Europe, correct? During the expansion, this cold reversal allowed this Arctic flower to expand across Western Europe. And it was found, the pollen from this plant was found in sediment records across Western Europe. So we're on board with that. I think I wanted to start out with that because we're just from knowing the climate change from the last glacial maximum to the Holocene. You just need a little bit of the background. So the debate has been kind of ongoing in the world of paleoclimatology to explain why do we have climate change in the past, what's driving it. There's different forcings, internal forcings, external forcings to the climate system that can drive these changes. So paleoclimatologists, we spend our days trying to figure out what is causing these changes, these cold reversals, warming, drying, becoming more wet, greening, etc. And just a few, maybe a decade ago, a new idea came on the, came out, and it was a publication by Firestone. What year was this?
The paper,
the original paper,
came out in 2007, although there was a book and that came out in 2006. But the real attention focused on the paper that came out in 2007.
Then in 2007, Firestone et al. Proposed something drastically different, or a whole new idea for the potential cause of the onset of the Younger Dryas. And using data that they had gathered around the world, they put together a hypothesis that a impact had happened at the boundary of the Younger Dryas. And this impact led to destabilization of the ice sheet, a big, gigantic meltwater pulse, and this changed ocean circulation in the North Atlantic, leading to a rapid climate reversal. And so Firestone essentially suggested that something external to the climate system forced it to change, and that this forcing perhaps could explain other things they'd seen in the fossil record and charcoal record, sedimentary records around the world. So this was highly controversial because for a number of reasons, and that's why I brought Dr. Holliday on the show here to talk about. And I've been following the story because when I first heard it, I was intrigued, let's say. I was always intrigued by the idea of extraterrestrial meteorites causing changes on Earth when I first learned about the dinosaurs and the Chicxulub crater in Mexico. But this is a little bit different. It's not as clear-cut of a problem. It's not as clear-cut of an issue, namely because there isn't a meteorite impact at the Younger Dryas boundary that can be attributed to a meteorite. So eventually, after a few papers, Dr. Holliday here wrote the beast, you call it, the comprehensive refutation of the Younger Dryas Impact Hypothesis. And you critically evaluated the evidence for this impact hypothesis put forth originally by Firestone in 2007, although there were a few other publications, and maybe we'll get to those after that. You evaluate it, and you say you dismiss it and you refute the evidence given. So I want to give you a little bit of time here. Can you explain in a nutshell why you don't believe the Younger Dryas impact hypothesis? What leads you to say that?
We'll begin at the beginning when this idea came out. It was the first thing that happened I guess it was the spring of 2007. I guess Firestone gave a talk at the American Geophysical Union meetings in Acapulco and presented this, although there was a book before that. But that paper at the AGU meetings got a lot of attention. And I heard about it. And then a few months later, the paper appeared in Proceedings in National Academy of Sciences. And I was intrigued. I mean, a lot of us were, my colleagues in different fields. I've spent most of my career in archaeology, particularly the earlier part of the archaeological record in North America, so-called Paleo-Indian archaeology. That figures in the impact hypothesis. I've also spent a big chunk of my career as a quaternary geologist studying the geology, particularly of the last, let's say, 20,000 years in North America. And I'm not a paleoclimatologist, but that's, all of us have that interest. If you're a quaternary geologist, if you're a Paleo-Indian archaeologist, or any kind of archaeologist, those are the big questions looming over everything is, what was the environment doing? Not just climate, but all aspects of the environment. So this paper came out, and it proposes, among other things, an explanation for the extinctions. As you know, there was a global extinction, the late Pleistocene extinctions. Mammoth, for example, became extinct, mastodons. In North America, the genera of mammals became extinct, but it was a global. I was very familiar with that because it's been a component of the archaeological discussions too, because, what happened? Why was this extinction? Why did this extinction take place? And one of the arguments is that people were responsible. So, and I knew a lot of the key players there. So those two things, extinctions, the Clovis record, and then the younger, an explanation for the Younger Dryas climate reversals. I followed that literature as well. So I was pretty familiar with this, as were many of my colleagues, and got our attention. And so a lot of us started thinking about it. There were proposals of different kinds of indicators in the geologic record, microscopic or geochemical indicators. And I got involved in collecting samples for that. Pretty quickly, well, from the onset, I was skeptical. And there are two key reasons why I was skeptical. I knew the archaeological record. And in the paper, in the initial paper and in subsequent paper, there was a discussion of the mysterious demise, in quotes, of the Clovis, so-called Clovis culture. Now, what that's referring to is a very distinctive artifact, a spear point, commonly associated with mammoth kills. And we're all familiar with this. They're kind of a hallmark of one of the hallmarks of the paleo, part of the Paleo-Indian archaeological record. I've worked on Clovis sites. I know the sites, some of the sites mentioned in the paper, and I know the archaeological record. And there never in my 50 years now have I ever heard anybody talk about some sort of mystery. What happened to Clovis artifacts? The world is full of artifacts, right? Humans make artifacts. We've been making artifacts for a couple million years. We still make artifacts. The cars going by my office, those are artifacts. And so this notion of a stylistic change being the result of some sort of catastrophe, it was just, as far as I was concerned, it was just wrong. And in particular was this argument that this artifact style mysteriously disappeared, and then there was a gap in the archaeological record. And I knew that was wrong, absolutely, demonstrably wrong. And it indicated to me that the people involved in this hypothesis weren't doing their homework. And then the extinction record, it varies in time and space, continent by continent. The timing of the extinctions varies. Which animals became extinct varies. North America, South America, Asia, Europe, Africa, it's varied. So a single event, comet, any kind of single event, it doesn't explain that. And neither have the proponents of the hypothesis. They've never explained, why is the extinction so varied in time and space? And in any one place, like in North America, the extinctions began thousands of years before the impact hypothesis. Now, a number of the extinctions are within a window of about, let's say 14,000 to 12,000, with the impact being roughly in the middle, proposed impact being roughly in the middle at 13,000 or 12,900. So the notion that all those animals became extinct all at the same time, it's just simply not true. So right there are two things that I knew right off the bat
Hmm.
simply didn't hold the water: the extinction argument and this extinction of Clovis culture. Then the other part of that, then another premise. So there were three premises in the original paper: demise of Clovis, the extinctions, and then the Younger Dryas itself, this mysterious event, cooling event. Well, as I said a while ago, I knew it didn't get cold everywhere. There's all sorts of evidence for that. And then as the years have gone on, as people have pursued this, what you could see now in the literature is that older glacial, interglacial cycles, no one is identical. They're not cookie cutter. Each cycle has its varies in detail. And you're a climatologist, paleoclimatologist. You know how that works. There are broad similarities, but it's never the same, right? It's never identical.
Bill
And
Ruddiman. Bill
well,
Ruddiman's done a lot of work on comparing those interglacials.
yeah, there are all kinds. Yeah, again, as a result of the initial recognition of this rapid climate change, really pushed a lot of research. And there's quite a bit now, particularly ocean cores, that show that coming out of the previous glacial interglacial cycle, roughly 130,000 years ago, there were some cold spikes. Timing is not identical. None of these things are cookie cutter. And I saw a paper recently, I think several glacial cycles back. Same thing. When you look at just the record of warm and cold, you see, maximum cold, and then it gets warming, warm, and then there's a reversal. Again, the timing varies, but it seems like that this is a normal component of deglaciation, of the shift from full glacial to maximum cold to maximum warming. It's not a smooth curve like we used to think. There are flip-flops going from one to another, which makes the Younger Dryas somewhat less mysterious. It was still dramatic, but it seems like it's part of the story as you come out of it. But to put it another way, you don't need some extraterrestrial event to explain this, because then do you need that at the end of every glacial cycle? Do you have to have, by coincidence, a comet arrive to do that? And none of these premises, well, they're not valid. For one thing, the idea that the extinctions were moment in time isn't valid. And that this disappearance of Clovis and population disruption, it's just the archaeological record just simply doesn't show it. So those are the things that raise a lot of red flags for a lot of us. And we've been debating this ever since. There have been a series of papers. I've been part of some, and then there have been others criticizing the impact hypothesis. And then the one that you have there is the most recent and most comprehensive. But there were other papers.
Other papers. And I do have a couple of those I want to get into with you, because I tried to look through and find some of the interesting examples and to talk about. But for the listeners that may not be, let's say, paleoclimatologists, and we're using the word interglacial, glacial impasse, and I want to just talk about that a little bit more, because essentially what you're saying is the Earth can generate internally nonlinear feedbacks. Fine. And these rapid events, what I would call nonlinear, so gradual warming or cooling, then we have a change up or down. And so what you're saying, in other words, is there's plenty of mechanisms on the Earth during these climate change events that can generate nonlinearity. We don't necessarily have to bring in an external forcing like a meteorite impact to generate that. And then if we invoke that hypothesis, then now when we look in the past at these rapid climate change events, are all of them essentially driven by extraterrestrial, forcings? And that's just there's no support for that, because, well, I mean, I'm not going to say no support for that, but we just know so many other mechanisms that could drive these nonlinearities, these feedbacks, number one, like ice cover and other things like that.
And I'm sure you would test this. We don't necessarily know what we don't know what drives all the various flip-flops. You've seen the ice curves, the ice growth curves.
Mhm.
They're really jagged, right? And when I first started out in this 50 years ago, 65 or 55 years ago, in the textbooks, the glacial interglacial cycles were just smooth curves. And we know that is absolutely,
Yeah.
we have more data, right? We have more
Yeah.
data. We don't necessarily know the mechanism for every little flip-flops, but it's very clear that there's all sorts of irregularities, meaning it's not a smooth curve.
Right. Okay.
You don't need these catastrophes. You don't need catastrophes to do this, because it seems to be a regular part of the climate system. We don't necessarily know what's driving all of this, but it seems to be intrinsic to the climate system.
Mm-hmm. Paleoclimatologists, their goal is to figure out what's driving the climate system.
Yeah.
There's a lot of mysteries in that. And just what I mentioned earlier, I forgot to define. Interglacial is when we say warm period. Glacial is cold period. When we're talking about basically since the Pleistocene, like 2.7 million or something years ago to present, when we have these distinctive interglacial to glacial cycles, that's what Vance and I are referring to. And when they cooling and warming between that isn't gradual, is what we're saying. It can be rapid sometimes, just to clarify. And what you bring up too, this just jogged my memory. The Younger Dryas cooling event is very distinct in the Northern Hemisphere in the Greenland ice core. Can you talk about what's the Younger Dryas look like in the Antarctic ice cores?
That I don't know.
I don't think it's in there. Am I wrong?
I think it is.
Is it?
Boy, you got me on that one. I can't. You're the climatologist.
Yeah. We're both the climate. I don't do, but I believe looking back.
Yeah, I should know that. I know that as we were talking about earlier, the cooling, rapid cooling is certainly not everywhere. I think climatologists, the ones in fact, one of my co-authors, and I should mention that paper you talked about, there are 12 of us. I certainly did not write a lot of that by myself. And climatologist has a lengthy discussion in there and makes the point that something seems to have happened at 12.9 climatically, but it varies tremendously, the direction of the change, the magnitude of the change, depending on where you are around the world.
Yeah, the Northern Hemisphere versus the Southern Hemisphere versus Alpine versus,
But in a very general, more broad scale, it's not necessarily the Younger Dryas. You do see more or less synchronicity around the world in terms of the ice age, the glacial cycles when the Earth was colder and you had a lot of glacial ice, and then the interglacials like we're in now. The Earth is warmer. We still have some glaciers, but nothing like we had before. That overall trend is very clear globally. North America, the Northern Hemisphere, the Southern Hemisphere, it's very clear that they were in sync, which is why I'm thinking there was some kind of spike in our ice core. But boy, that's a good question. I don't recall the answer.
Okay.
Homework to do.
Yeah, do a little bit of homework. And there might be issues also with the resolution of those ice cores down there, like Vostok and everything, because it may not be highly resolved through the Holocene, late Pleistocene to resolve. The amount of ice up on Greenland and the layering, the age model is like so good. They can get down to almost a year.
Yeah.
And that's why we can tell that it's a very rapid event, because the layers in the Greenland ice core give you annual changes.
Like tree rings. Yeah, you can really see them.
Very much like tree rings. So as I was going through your papers, and there's just so much, and the huge papers out there and other things, I did find an interesting one that I thought was, maybe not necessarily the smoking gun, but I thought was, hey, this is pretty interesting, something we need to talk about. And it started with me finding this Petaev et al. 2013, the platinum anomaly discovered in the Greenland ice core and now that we're talking about that. So just a little background, a paper in 2013 by Petaev. I hope I'm saying that right.
Petaev.
Petaev. They analyze platinum, iridium, and aluminum concentrations in the ice cores from Greenland. And they found this anomaly in platinum, an increase in the concentration of platinum relative to aluminum at that Younger Dryas boundary near there, right around 13,000 years ago. And they published a paper stating that this might be evidence of a extraterrestrial impact, because in meteorites, they're more enriched in platinum elements like iridium and osmium and other things like this, because they haven't differentiated like the Earth has. And so when we use platinum elements as a proxy for meteorites, specifically the Chicxulub crater at the KT boundary, iridium was like the smoking gun for that meteorite impact. So by extension, Petaev, speculates or proposes a hypothesis that maybe this anomaly in the platinum group elements in the Greenland ice sheet at that boundary could have been a extraterrestrial impact. Maybe I know there was a follow-up paper by Sun later on, which I want to talk about. So in Sun, I guess, before I let you go, Sun in 2020 addressed this extraterrestrial explanation for the platinum anomaly in the Greenland ice core by proposing that it could be an anomaly driven internally by volcanic eruptions on Earth. If you looked at isotopes and you looked at volcanic activity around the world, and I think this is something very understudied, is the Younger Dryas boundary also coincides with the Locher See eruption in 12,900 years ago in Germany, a massive volcanic eruption. And so Sun et al. In 2020 proposed that the Locher See eruption was the driver for these platinum element group anomalies in the Greenland ice sheet. And this then would help maybe explain why we see some weird extinctions in the Western Germany or Western Europe or something, because that would cause localized, perhaps, extinction or bottlenecks, let's say, of populations. So what do you think about the if I was out there and I saw that platinum group anomaly in the Greenland ice core, I would have thought, hey, that's pretty solid evidence. Maybe we could say they don't need a meteorite impact. It's a chondritic carbonaceous meteorite burned up in the higher atmosphere into little bits. It doesn't need to make an impact, and peppered Greenland ice sheet with the platinum groups. What do you think about that? You don't think why don't you think that's good enough of an explanation?
Either in that paper or in another one, Petaev says, I think they offer that in the initial paper as a possibility, but I can't remember, either buried in that paper or in a subsequent paper, he says he doesn't think it's an impact. If it was an impact, it was not a big one. It was not a global impact, that it was much more localized. And then relatedly, I can't remember the name of the paper. I'm just drawing a blank. We talk about it. I quoted at length in the paper.
Is it the Hall's Cave? The Hall's Cave study?
It was a paper looking at the timing of the platinum anomaly and the onset of Dryas, and they see an offset of some significant number of years. Again, to remind your readers, in the ice cores, they count annually. So they have a really good picture, offset of about 30 years, I believe, in the timing. And so the timing is off, trying to link the platinum anomaly with the proposed impact, and that the platinum anomaly isn't necessarily a smoking gun. Now, then going to the Locher See, I think the timing of that is off. Because I know it's been kicked around as a possible explanation, but I think that the timing of that is off. They're not identical. It's the 12.9 for the impact and the dating of the Locher See. I think there's some variation there.
Yeah, it would be you couldn't get annual dating on dating volcanic ash layers if you're using potassium argon. So you're going to have a huge error. So that's interesting.
Or radiocarbon, yeah.
Or radiocarbon.
Yeah, you're going to have a plus or minus.
I think they had a paper. The paper that I looked at for that date for 12.9 was, I think, 1999. So maybe
Yeah, I think there's been
they've
more.
been updated up on that. But that was something I was not aware of, this big explosive volcanic eruption in Germany.
I know,
Right.
that surprised me too. Yeah,
I
you're
mean,
sitting on Hawaii.
yeah, we're sitting out here and you don't think about what Germany being, I believe it was Western Germany. And, think about the Neanderthals or early human settlements
Yeah.
there, right there. And,
I mean, you do like in Italy, of course. There was a huge. I worked on some Paleolithic sites in Russia that had 30,000-year ash out of the Campanian volcanic fields near Naples. That son of a gun was dumping ash. I mean, a couple of inches thick as far away as Western Russia, all across. In fact, that apparently did have an impact on Neanderthal populations. But that one's obvious. I mean, you see the ash all over, and as I said, we had it. So, yeah, Italy, all around the Mediterranean, you'd think, oh, sure, there's volcanoes all over the place. But Germany
yeah,
was
wow.
a eye opener to me too.
So that's something that they don't consider, when you hear about this Younger Dryas Impact Hypothesis, is that eruption. So I dug into the literature, even I think a little bit more in detail, because I was like, I'm going to find something in here. I'm going to find a little hole. And I was looking even further. And one thing, Sweatman, they wrote a paper, Sweatman, Powell, and West wrote a paper that was entitled Rejection of Holliday, my guests, et al.'s alleged refutation of the Younger Dryas Impact Hypothesis. So I dug through Sweatman's paper, which I'll have links to all these papers at the bottom in the description of this interview. They mentioned that in the Sweatman paper, they mentioned that Sun in 2020, the one that proposed the Locker-Say eruption of 12.9 as an explanation for the isotopic and platinum group anomalies in the ice core, they say that they omitted, the Sun paper omitted samples from Hall's Cave that at the Younger Dryas boundary that would have corroborated their findings. They said that Sun, because I didn't mention the Sun paper, in addition to analyzing Greenland ice, they also analyzed sediments and cave deposits around the world with Younger Dryas boundaries in them. And Sweatman makes the claim that they omitted samples from the Hall's Cave record. Is that true?
I don't know. Those are the kind of things. No, I don't know. Those are the kind of little nitty gritty she said kinds of things that I can't. You'd have to go to the original papers and the original authors. I mean, those Sun et al. are the ones that need to refute that. Or whatever.
I mean, it was an interesting, because I think they cited personal communications or something like that. I'll double check it, but it was
it's not published. Whatever the information have isn't published, and that, to me, that's completely off the board until it gets out and gets published. I mean, that's what we're in this business for. So I can't.
Yeah, what a strange. It was like they had this, Sweatman and the authors had knowledge that Sun didn't analyze one sample from the boundary. It was like, what? I was like, that is such a strange. I've never heard anything. And even if they did analyze it, and even if it did have the anomaly in it, the Younger Dryas, and like just you mentioned, the extinctions, the climate change event isn't synchronous around the world. It doesn't explain.
Yeah.
So even if you added that and it somehow matched what you said, it doesn't necessarily prove anything either way.
Yeah, that information needs to get out there. But there's nothing we could do about that, right?
Yeah.
What's going
on? The
on?
lack of information that they're aware of that wasn't published, but then they got it published to say that as so.
Well, yeah, of course, when you have these responses, the responses don't go through peer review, which is a little aggravating, because you can say whatever you want, and it just goes on and on and on, which, that's a component of this debate that drives a lot of us crazy.
Yeah, I can imagine. These papers are beasts. They're huge. There's so much literature to go through. And that's why I think it was interesting to have you on the show, is like have you come on here and just tell me. It's just been such a hot debate. You see it on like big podcasts. People talk about the Younger Dryas Impact Hypothesis like it's like set in stone, or it's
Yeah,
like,
and that's very aggravating because they don't people. I mean, we've published that in that paper a lot, but we've had previous papers where we itemized all these problems. Like I was saying, they claim that Clovis mysteriously disappeared, and yet the archaeological record shows that's not true. And yet we've pointed this out, and they never deal with it. They never deal with the issue of extinctions. How does an impact explain extinctions that varied in space and time? These things are never dealt with, and they're still out there. These are still really significant questions that are still out there that the impact proponents just ignore. And that's what drove this paper. I mean, that son of a gun, that took a better part of 2 years. And I have a lot of other things I'd rather be doing. Explaining again, not the first time, not the second time, not even the third time, what some of the problems are with the impact hypothesis. And they're never, some of these key issues are never dealt with. And related to what you were just talking about, smoking gun indicators. Nobody has come up with a smoking gun indicator in terms of a chemical or particulate indicators. And as you said at the outset, there's no crater. I mean, I guess there could be a crater out there somewhere, but nobody's come up with that either. So,
and they do, just to be devil advocate on that crater, because that was one that I was like, okay, you can explain that one away. Sweatman and other people that are in the camp of the impact hypothesis, they propose, just to be their voice here, that there's no impact because it was a chondritic carbonaceous meteorite that broke up at higher in the troposphere or something, and then burned up and destabilized the ice sheet if it did hit it, thus not leaving an impact on the ground. That's their explanation for that. Again, that's another one where there's absence of evidence. Is there evidence? Like, see, there's no meteor because we know like that it's chondritic.
And
so
other papers, every now and then a new crater is discovered. And this has happened now several times in the last few years. A new crater is discovered somewhere. And immediately, this must be the Younger Dryas Impact Crater. And it turns out not to be. So on the one hand, a lot of the proponents have fixated. There's one that was just exposed under Greenland, the Hiawatha crater. It was like, oh, this must be the Younger Dryas crater. Even though some of their arguments don't require a crater, but then when a crater appears, and then they propose, oh, this must be it. And then that crater literally turned out to be 58 million years old, not even remotely close.
Yeah.
So it seems like they're trying to have it both ways. That, oh yeah, this must have been the crater that produced the Younger Dryas Impact. Oh, but we don't need a crater. I'm not a craterologist, impactologist. One of the co-authors on that paper, Mark Boslow, spent his career dealing with extraterrestrial impacts. His argument is that the mechanisms they propose don't meet any sort of required or any sort of physical standards in terms of what happens when an impact hits the Earth, what happens when there's a disruption of the impact in the atmosphere, that the explanations don't fit what we know about how extraterrestrial bodies, how they act in the atmosphere, either when they explode, when they blow apart in the atmosphere or hit the ground. None of the explanations so far. In fact, I think Mark goes into detail in that in the paper. What we know about how this process works, the physics involved. For example, like the Tunguska event in Russia.
Yeah.
There's a lot of studies that. Anyhow,
which was the early 20th century. I think it's Tunguska crater. Early 20th century Russia impact. It was widely studied.
Apparently an airburst. But
an airburst
did leave it. Anyhow, so I mean, but the point is that none of the explanations so far meet what we know about the physics of extraterrestrial bodies, and so they don't yet have a true coherent explanation for what happened. Now, that's, I guess, in a sense, you don't necessarily need that if you can find some kind of physical evidence on the ground, either in some sort of particulate matter or geochemical. And then another thing I pointed out, there's simply no geomorphic evidence. In other words, in the Earth's surface systems like rivers and glaciers, lakes, there's no disruption whatsoever of any of those systems anywhere that indicates some sort of catastrophe. The glacier, I mean, we have a really good record of what was going on with the glaciers as they were retreating. The big ice sheets were already well underway, retreating at 12,900, and there's no evidence there was some sort of cataclysm that affected the ice sheets as they were retreating. There's no evidence of some sort of cataclysm affecting the river systems, the lakes up in that part of the world. There's no physical evidence. And so most of the evidence ends up coming in little tiny particles of dust and geochemistry. This major cataclysm that supposedly affected either all of North America or parts of North America and other continents. But this event, there's no evidence for it except at the microscopic level. And why is that? How does that work?
That's an interesting way.
It's a point I've made and some others have made. One of my colleagues years ago made a good comment and says, what if there was an extraterrestrial, this is the reverse. What if there was an extraterrestrial impact that had no terrestrial impact? In other words, what if a comet hit? Let's assume, okay, what if a comet hit and then some people noticed it, and then they went about their killing mammoths or whatever, and it just didn't have a cataclysmic impact on the climate system.
I see. Yeah.
I mean,
that makes me think, when you bring up the Tunguska event, if you took like the temperature records and precip records and integrated them across Siberia, and then you, like maybe the last 500 years of those, if you had them, and you put that event for the Tunguska, it would maybe be like the month after it, or the few months from the dust settling, and tree cover changed surface color albedo or something. And it would be nothing. It would be a tiny little blip over the climate history of Siberia. Almost.
Yeah. And here in Arizona, we have the meteor crater up near Winslow, Arizona. And it's, I think, 60,000. And then I worked on one near Odessa, Texas, the Odessa crater, and it's 40,000. God, I did the dating. I can't remember what it was, but there's no real record of that in the bigger geologic story locally. But so again, you'd think there'd be more out there in the more obvious evidence. Now, conversely, too, I should point out that some of the indicators, the particulate material that they have used to suggest it was an impact, shows up at other points in the geologic record since the 12,900. There's no evidence of impacts. So that's, again, they have no really unique indicators for that
Interesting.
The time period.
Let's talk about these other indicators. Nano diamonds. I'm a sedimentologist. I've never seen a nano diamond. I study the Holocene and the Pleistocene. Why do you have an issue with nano diamonds? What's the issue with nano diamonds and as a proxy for Younger Dryas?
Nano, of course, is tiny, I guess.
How big is a nano diamond? Is it less than a micrometer? Or if you look at the sedimentology?
They're really small. But there's a lot of different kinds, apparently. There are lots of different ways of creating them. And there are lots of different species. Our paper goes to that. This geochemistry was not my strong suit in graduate school. But it turns out there's lots of different kinds of nanodiamonds. There's lots of different ways of producing nanodiamonds. Impact is one way, but so far there aren't any nanodiamonds that are clearly, uniquely, in the research that's been published, there's nothing that's clearly or uniquely tied to some sort of extraterrestrial impact. So over and over, these different so-called indicators have been proposed as smoking guns. I remember when nanodiamonds came out. Oh, we've got nanodiamonds. It has to be an extraterrestrial impact. And then some geochemists got involved. In fact, people on our paper said, no, they're all different kinds of nanodiamonds. And in fact, some of the research has not been reproducible for some of the nanodiamond work. Without going into detail, I got involved in a study where we collected samples for, among other things, nanodiamonds at a site in Texas. And I couldn't find anybody to do the work. Apparently, according to the lab methods, something like 120 steps. It's like, I couldn't find a lab anywhere that was willing to take this on. So, we're getting into some pretty esoteric analyses.
I was just going to ask you, how do you measure nanodiamonds? Like ICP.
First of all, you have to extract them.
You have to extract them.
Incredible method. That's so anyhow. There's what do they call them? Magnetic microspherules that are supposed to be impact indicators, but I mean, they're literally magnetic microspherules are being produced today from industrial and as a part of industrial pollution. So they're not unique to terrestrial impacts. There's no iridium.
Yeah, no iridium. That is something they mentioned in the Petaev paper. Yeah. Iridium is the platinum group element that's used to demarcate the KT boundary, the dinosaur impact.
The dinosaur extinction.
But they used platinum, and it was a platinum anomaly in the Petaev, and then they looked at osmium isotopes in the Sun paper, which are all, for those that are not geochemists, the platinum group elements are very unreactive. They're very difficult to measure with even our modern techniques. And so just those alone, let alone nanodiamonds themselves, is very difficult to measure. Okay,
one of the very first papers, contradictory papers that came out so that the original paper came out in 2007. Within a couple of years, one of the co-authors on our paper, he and some others looked for iridium in samples from all over the world, iridium right at 12,900. They couldn't come up with any.
I tried to.
Was something of a surprise. And then just in general, there's issues of reproducibility of measurements between labs. That's a cardinal rule in scientific method, is reproducibility of results. And there's been a lot of problems with reproducibility of results. Yet another issue for a host of these methods.
A bunch of these different things.
Yeah.
So now if we take the Younger Dryas impact off the table, let's take it off the table, what would you say is driving? It's still a mystery, this reversal, this nonlinear response to this rapid reversal cooling starting 12.9 in the Northern Hemisphere. What caused it? What do you think caused it?
Yeah, it's a paleoclimatologist. One of the things that's been out there, I'm sure you're aware of, is having to do with the melting of the ice sheet separate from the impact. The ice sheets were disappearing rapidly at this time period. And so there's tremendous amount of fresh water, cold water, dumping into the Arctic around North America, particularly northeastern North America, the biggest ice sheet, dumping tremendous amounts of water into the Arctic Ocean and the North Atlantic. And which is something that would happen cyclically, right? At the end of every ice stage, the same thing's going to be happening. You're dumping tremendous amounts of cold water into the world's oceans. And assuming that the glaciers were more or less the same size and shape, which they probably were, you probably have the same amounts of water going the same places every time, and so the idea is that there's cooling of the oceans, and then that triggers global changes because of the so-called conveyor belt of warm water that we have in the oceans today shuts that down. All this tremendous amount of cold water being dumped into the oceans. So it seems to me that that's a perfectly plausible mechanism. I'm not an oceanographer. I'm not a paleoclimatologist, but you see that. I'm sure you're familiar with some of that literature. There are a lot of papers that have dealt with that. For a while, there was an issue of timing the retreat of the ice sheets. The ice sheet locations would have blocked the release of a lot of the water into the North Atlantic until later. But I think some of the revised dating of ice retreat suggests that the timing actually works now. you have ice retreated far enough to allow a lot of meltwater to go into the North Atlantic down the St. Lawrence Seaway. But there's also an argument, too, of meltwater going north out of Canada into the Arctic Ocean that could have a similar effect.
I've heard both. I
Yeah.
think it's pretty settled that the onset of the Younger Dryas is caused by the shutdown of deep water formation and the global conveyor belt, which is driven by the North Atlantic deep water formation,
Right.
mainly. And so that's kind of settled, but and that was caused by this pulse of water, probably from, I think Lake Agassiz empties or something through the Labrador Sea. And then there's some data that maybe there's a river up through the Canadian Arctic that might have pumped some water. But that still leads us with, then what caused, is that big meltwater pulse? It's just a random ice dam break, just happens to break, or, isostatic rebound is altering the landscape, and that happens to just change the outlet at this one spot. And is that kind of what you're thinking?
Yeah, I mean, the whole ice retreat system, there's less ice on the landscape. You have the land rebounding. You have just tremendous quantities of water that one way or the other are going to end up in the oceans, right? They may get stored in a lake like Glacial Lake Agassiz, but there are a series of those lakes as the ice retreated. And then you have a threshold of some sort crossed, and all that water dumps into the North Atlantic and the Arctic Ocean. I mean, it seems plausible. It's coherent. One of the nice things about it, you can make a pretty coherent story. And the problem with the impact hypothesis is it's not particularly coherent, at least to my view. So much of it sort of falls apart, at least as far as I'm concerned, when you start digging into it. Like the basic premises I started talking about. It just doesn't work for some sort of catastrophe, as far as I'm concerned. There's too much that remains unexplained or unanswered. Again, this is what happens. Like that, you had the paper, the refutation of our refutation, and then we responded to that
with another one. Yes.
Yeah, this could go on forever, right?
This is a rebuttal of Sweatman House. So you have the rebuttal of the rebuttal.
And their rebuttal, it just touches on a few things here and there, and not very well, as far as I'm concerned. They don't deal with all the issues we raised. No paper has ever dealt with all the fundamental issues. Since this is going back to the first real critiques came out in 08, 09, and 10, right in there, 8, 9, and 10, after the 2007 paper. And to this day, and from then on, no paper dealing with the impact hypothesis has ever dealt with the fundamental critiques that we've brought up over and over and over. And that's the thing that's so frustrating about it is, we keep raising these issues and a lot of it gets ignored.
And that's kind of why I wanted you to come on here is I see that this is happening, and I just think, I feel like it's easier for people that might Google this just to hear you talk about it or get a perspective that's not in a scientific paper. Maybe they don't have access to scientific papers if they're in public.
Yeah, that's true.
And so you have that issue.
Who's going to sit down beside you and me and read a 77-page paper?
It was, yeah, exactly. And it's I tried going through, I'm sitting there last night doing homework, trying to go through this. And I'm like, this is just so much to touch on and a million different questions and citations. Not just
it's just, yeah, I know.
It's a lot.
It was
now, if we have this naturally, so we have a pulse of fresh water to the North Atlantic, it shuts down the conveyor belt.
Yeah. Cold
fresh water, because for the people listening, during the last glacial maximum between 22 and 18,000 years ago, sea levels were about 125 meters lower than present. Large amounts of that ocean water are trapped as fresh water on continental ice sheets. Now imagine losing that over a course of about a few thousand years. And during periods, there's lakes being formed. There's big liquid pools of water on top of the ice sheet, perhaps as it's waning. And this, okay, we're settled at that. That's probably driving it. Even we don't have to talk about what caused that to go out there. Just with that meltwater pulse alone, that's going to drive that climate event. It could just be a random geomorphic ice dam break. Then this would further explain why in some areas perhaps we see bottlenecks, let's say, in megafauna populations. We see some, Western Europe, we see rapid climate change. This is clearly going to change, distributions of plants and animals. And that's going to drive, let's say, regional changes in populations, maybe human and animal. And that's would then help explain their issue that, there's this, apparent, there were megafaunas all over in the last end of the Pleistocene. We get to the Holocene, and except for Africa, all the megafauna go extinct. Well, we can explain perhaps some of that with just natural climate change and humans without even invoking the extraterrestrial hypothesis.
Exactly. That's the thing.
That's the key. Yeah. And we don't necessarily, I think using the word extinction may be difficult. Like, I think that's maybe a point that I would have I don't know, split hairs on, because maybe you can make the argument that populations don't necessarily go extinct, but there's a large decline in populations, bottlenecks. Because like the mammoth, we know existed up in Siberia as a pygmy mammoth until 5,000 years ago.
Yeah.
So that didn't technically go extinct until 5,000 years ago. But we know around the Great Lakes in the Midwest, mammoth is gone by 10,000 years ago, 11,000. And so it's not necessarily extinct. And maybe there's some populations at 8,000 years ago high in the Canadian Arctic we don't know about yet. So I think that would maybe be a point I would split hairs on, because you mentioned in there, you're there's no evidence for extinctions, but maybe there is some evidence for bottlenecks of populations.
Yeah. That's paleobiologists of one kind or another should be doing more on that. And I think some people are. It's easy for us to say that.
Yeah.
Should be studying that. And maybe people have, but although, they're gone today, the mammoth's gone, mastodon's gone, saber-toothed cats are gone. Camels, there were camels and horses.
Sloth, the short-faced bear.
There it is, all raft of. They're all gone. But again, the timing, it does vary. It did vary.
It does vary, yeah. And if you have mastodon populations, I know in the Great Lakes, I think are dated to 11,000. I'm just looking at dates for that. And so that's after the Younger Dryas. And so we have mastodon populations around the Great Lakes, perhaps.
I guess the question would be, again, this is sort of inside baseball, but are you looking at the calibrated radiocarbon or uncalibrated radiocarbon?
I always look at calibrated.
Well, okay. Well, good.
Yeah. That's a good point to bring up too.
Depending on what you're reading.
Mm-hmm.
Yeah, I think there's been some recent papers that shows that that even in North America, the extinction event was not a light switch, or a light being turned off, boom, by mammoths, by mastodons. And in fact, there's even evidence. I can't remember the name of the term. There's a kind of fungus you can recover from lake sediments that is found only in the gut of certain mammals like mammoth. And so essentially what you're looking at is a record of poop getting into the lakes. And they can see that a decline. I know in the northeastern U.S. there's been some work on this. You can see a decline beginning well before the extinction. So what seems to be happening, at least in some places, that the animals are already on their way out. And so then on top of that, maybe some kind of stress. Some people would argue human hunting. Others, as you were just saying, climate change, or very rapidly changing climate, just is the sort of the last straw, and the animals can't survive that. So yeah, I mean it's a complicated issue, that's for sure. The demise of all these animals, and again, it doesn't make sense to me to look at all the data that's out there and decide that it was just a comet from space falling on the Earth's surface is the answer. Just it doesn't work at all, not remotely.
That brings up a point that I think we should address is how in the heck do we determine population variability in megafauna 14, 12, 13, 12, so on and so forth, thousands of years ago? And you brought up the proxies of the fecal stanols and the fungal spores, which is an interesting new route. We can analyze biomarkers essentially that are produced in mammalian and other species poop. And this washes into water bodies, or we can analyze it. And also environmental DNA is going to be a huge one,
That's
Vance.
going to be big.
It's going to be huge, which I have proposals in my mind right now for this, for other places. What I do want to talk about is a classic site, though, that we have a lot of information on megafauna and their changes through time. And this is the La Brea Tar Pit.
Yes, right. Yep.
So the La Brea Tar Pit we need to talk about. So this is in Southern California near LA.
In LA.
And in LA. It's in Los Angeles. Go check it out. And it's a petroleum tar pit, oil seep. There's a lot of petroleum in that area. That's why it was developed early on drilled for oil. And these pits would trap animals in them, these tar pits, and they would fall and their bones would be preserved. And the La Brea Tar Pit's been excavated quite a bit, and the skeletons have been removed, analyzed, species assembled, put together. And from what they found in the La Brea Tar Pit, correct me if I'm wrong, Vance, is that a lot of the megafauna are gone in the tar pit before the Younger Dryas.
Right. You're right. In fact, I think one of the papers recent paper in support of the comment misstates the published literature. But all you have to do is to look at the diagrams. There's some just spectacular articles, I'm sure you've seen them, where they've plotted the frequency of saber-toothed cats, mammoth. They haven't done mammoth. From what I understand, they're going to do a whole separate paper on mammoth because they have so much. But all the other animals, it's very obvious that they're on the way out well before 12.9. It's a really spectacular record. There's probably nothing quite like it in the world, certainly not in North America. Really looking at populations. I mean, you make a very good point. It's really difficult to get at, and that's one of the very few places I know of where, you have all these animals coming in, but they can't get out, right? They come in to die, can't get out, as opposed to other sites that have other issues. But it's spectacular, and it clearly shows that the extinction was well underway before. And then I think there was even, I haven't looked at that paper in a while. I think there were even some hints of a few of the animals surviving after the extinction, but I can't remember which ones, and I may be wrong about that.
I'm sure, I'm sure there are small population bottleneck areas that, like the mammoth question. We know mammoths existed in the Arctic, Siberian Arctic, way until the mid-Holocene, but we can pretty much say they were extinct in North America.
I think that
for our purposes
used the term extirpated.
Or extirpated, or
from one area but not another. But the big guy.
Oh, that's the word for it. Yes, that's a technical word.
Though, it seems like for the most. Yeah.
This also brings up the KT boundary debate, which I got into teaching a class one time. In the 80s, in 70s, it was a big mystery why the dinosaurs, and when we say the dinosaurs went extinct, what I'm saying is the large-bodied, non-feathered, cold-blooded dinosaurs, like the T-Rexes, Triceratops, Brontosauruses. I'm not talking about the feathered, small, warm-blooded ones at that point, which would be birds, for those that don't know, which would eventually be, There's even debate now among paleontologists that if in some of these records, they show that these large-bodied dinosaurs were on their way out before the KT boundary, and that the KT boundary might have been the final straw that broke the camel's back type idea. And because they were so highly dependent on large amounts of biomass to feed on, and the T-Rexes fed on the Brontosauruses, and that kind of led to this cascade effect on the big land animals, which tend to be kind of preferentially susceptible to extirpation. Large-bodied animals on the surface is what I've gathered. I remember reading that. So even with that, there's a debate now that there's clearly no debate that there's an iridium layer. There is an impact, Chicxulub. It is dated to 65 million years ago. the iridium layers found across Western North America, it's above the last dinosaur fossils. But when you get into the details, nitty gritty, it seems like up into that layer, a lot of them were already extinct. And now the idea is there might have been issues with diseases and climate change because of the orientation of the plates that could have been actually driving the population decline pressures on these large body dinosaurs before the KT boundary. So right there, now we're already like, oh crap. Because before they found that Chicxulub crater, which was discovered in the 80s, there's all this discussion of what led to this thing. Yeah, and there was the Deccan traps is another one. Just like Younger Dryas Impact Hypothesis, there's a meteorite impact at the KT boundary supposedly, but there's also a gigantic volcanic eruption in the Indian subcontinent called the Deccan traps. That's another now leading hypothesis for the extinction of the dinosaurs, because I guess there would have been an enormous release of greenhouse gases that could have led to a forcing that, led to them going extinct. So just like Locker say and the thing, there's another internal catastrophe being generated by Earth at the same time. We don't have to necessarily invoke the outside world.
And we know how all the things that were going on as you come out of the last ice age. I mean, just tremendous rapid changes. And so it's no surprise. Now, the one issue that's come up there is that you don't see the same extinctions coming out of other glacial interglacial cycles. But again, the point there is that in general, they're similar. Cold period, lots of glacial ice, sea level goes down. You switch to warming, ice goes away, sea level comes up. Climate's changing. But in detail, they vary a lot. And that could be part of the issue. A particular combination of events and their rate of the climate change might have been the triggering factor. Just bad enough that you flip the switch and the animals don't survive it. So that's a tricky one. But there's actually literature on that. And as I said, not all of these. There are a couple of other extinctions over the last couple of million years. The problem is that we don't have the age control, the resolution anymore. When you get back very far, as you know, it's really hard you just can't know how rapid a particular extinction was, like we can with the evidence we have now, the stratigraphic evidence, fine scale stratigraphic evidence and dating methods that are very high resolution, very accurate and very precise. You don't have that as you go back in time. You're well aware of that. So anyway, it's a conundrum.
Well, it's good to tell, we want the audience also to know they may not be experts. And so I definitely appreciate the details. But yeah, that is that's what I wanted to talk about really with the Younger Dryas Impact Hypothesis. What else is, other things I kind of dug around into was other meteorite impacts. Like you had mentioned, we know there's craters around the world. The Tunguska, we mentioned early 20th century Siberia, not even a blip on the radar of climate for that event. It, left a radius several miles of an explosive event, barely a blip.
Not much of a crater. It was largely
not much of a crater.
Right.
And then you mentioned the one in Arizona. What's that dated to? 50,000 years ago.
50 or 60,000. Yeah, I'm drawing a blank right now. And then there's a slightly younger one in Odessa. And there's a crater there too.
And big craters. And the impact hypothesis crew even brings up the Kenneth Tankersley brings up a late Holocene impact that I'm actually familiar with in Kiowa County, Kansas, where this is between like about 1500 AD to 1000 AD. And there is a meteorite impact in Kansas that the Native Americans observed. And I actually had a piece of it's a paleocite meteorite. So it's an iron meteorite with olivine crystals in it. And the geology department at Kansas State had a piece of this meteorite. I didn't know it. I used it for teaching in class, but I remember it was from Kiowa County because it said on the sample. Turns out that is this paleocite that fell in southern Kansas, and the Pawnee had petroglyphs written all around where this crater was, where this iron meteorite had blown apart in the prairie. And I thought that was just another interesting, I just think something interesting to think about, that, these meteorite impacts are anomalies. They would have had if you saw one, you would have been like, oh, that's
absolutely
huge. And clearly, especially if you found iron bearing with green crystals in your Pawnee on the prairie, it would have been like, what, in pre-contact periods. But again, what I want to get, my point is, climate wise, nothing. This is like a blip. So meteorite impacts are natural to the Earth system. The Earth system has been hit by meteorites for 4.5 billion years. It does not seem like it's a very large forcing on Earth, except for maybe, with the exception, these massive impacts like Mount Everest size impacts at the Chicxulub crater. But that doesn't even explain how did frogs survive? How did turtles survive? How did alligators survive? Because frogs in the fossil record from prior to the KT boundary look very similar to frogs after. Frogs have porous skin. They're highly sensitive to temperature and precip, and amphibians in general. That's a big mystery. That's one of the big flaws of the KT boundary impact hypothesis, is it doesn't explain that a bunch of other animals didn't go extinct, that what you would think would have been more sensitive, like frogs, to something like that. That then is, my point again is, these impacts aren't that big of a deal to Earth, especially these minor ones. They're like maybe a blip in the temperature record, maybe a blip and maybe could explain extirpations locally if you have a big one, but so could volcanoes. And we know those things are going, blow up all the time around the world. And we know they have an effect that can last a few years at least, with the sulfur in the atmosphere. So you don't necessarily even have to invoke extraterrestrial. And so we have both volcanoes and extraterrestrial, and we have climate records in the volcanoes and extraterrestrial alone. They don't explain much of the variability we see in the climate. So there's internal forcings like ENSO, ocean atmosphere feedbacks, and other teleconnections that are linked by like this conveyor belt they create enough forcings in the climate system alone to drive changes. And they actually seem to be explaining more of the variability that we see in the record. Along with orbital, I want to say, if we're talking like 1,000, 10,000, 100,000 year timescales, the Milankovitch cycles, the orientation of the Earth's axis and its seasons to the sun, that is a primary forcing on 10,000, 100,000 year timescales.
Long term.
And so those alone are showing a lot more. They don't explain all the variability you see, but they explain a lot more of it. And we still want to emphasize the meteorite impacts. It's like this.
When you look at the long-term archaeological record of the Americas, you really don't see huge perturbations in populations. Now, once you start getting into organized communities, we have agriculture, for example. You start seeing hints of things like if there's drought for a few years, people move on. You see some of that, but again, that's normal. You don't need a outside forcing, and certainly for hunters and gatherers, which represents quite a long, big chunk of the record in the Americas, well, in the old world too. You really don't see a lot of evidence for major population perturbations. Every now and then you can, and I alluded to this a while ago, in a few places, huge volcanic eruptions. You do see evidence. There was a big one in Indonesia that probably had a big impact on populations of Southeast Asia. I want to say 60,000, but I could be wrong.
Yes, I know exactly. That's the mitochondrial Eve. There was a big, right around 60,000 years ago, there was a bottleneck genetically in human populations that coincides with this large tropical explosive eruption.
Right. Yeah. So you do see those things here and there, but certainly nothing I know of linked to a comet.
Yeah, and if the comet or the meteorite impact from the Younger Dryas did cause, let's say, a human bottleneck, let's say, a human population bottleneck, not necessarily extirpation.
Right.
Wouldn't that be apparent in the genetics of us at this point? And it doesn't seem, it seems like the bottleneck 60,000 years ago is apparent, but not necessarily anything, as far as I'm aware, at the Younger Dryas dated to
I'm
that
not
period.
aware. Of course, that's a good question. I know some people in archaeologists who know a lot about genetics. I should ask that. Of course, part of the problem is we don't have many human remains from that time period. Very few, and even subsequently, it's not until 7,000 or 8,000 years ago you start seeing a relatively sizable population of human remains, burials, intentional burials, and that sort of thing. But even there, I don't know. The DNA isn't often preserved. I should ask my genetically oriented archaeology pals if anybody's ever seen anything like that. Of course, you wouldn't expect the New World populations came from the Old World, but we don't know exactly.
Yeah, so there would have been almost a bottleneck just from that migration.
Yeah, and
the
there have been discussions of that, the migration. Of course, part of the problem is that the dating of the genetic story is pretty sloppy. I mean, just by the nature of genetics, they have to make all sorts of assumptions in how long or when a particular genetic anomaly happened. That's the word I'm looking. Mutation,
yeah.
and that's really difficult to date. So the dating is pretty imprecise.
And I think they also have to assume the age, how long people live. Like they put an average age, like lifespans, and then you put in average time for mutations, and then you can kind of backtrack ages. And I've looked at a little bit of that genetic data. I'm not a geneticist, and I really feel outside of my wheelhouse, and I try to dive into that. But I got a little bit into the North America because that's where my research was focused on, at least after the glacial period. And paper I remember reading shows that when there's new populations are expanding, there's like different clades or something. There's an evolution in the DNA as populations expand and they go into new areas. And I just remember reading that the paper showed that populations did that in North America following deglaciation. So like these, and so they made the argument that once you free up all this environment with no ice on it, you have these new environments for people to move into and populate. You have these huge expansions of population, and it just showed like the Younger Dryas time period, and then there's an expansion of population to like the mid Holocene. And so I was like, it's kind of what I thought it would have been.
And as you just get more people on the landscape from zero, whenever people first arrived in population, because you can even see evidence of increasing population beginning with Clovis, I mentioned, pretty widely scattered on the Great Plains and in the West, probably more common in the East. Then the subsequent groups, Folsom, so-called Folsom, and some of the others, there's a lot more people on the landscape as, more people making more people. So you start seeing evidence for regionalization of artifact styles and things like that pretty early on. In fact, the argument, one of the arguments going back to one of the first things I said is that, Clovis was wiped out and there was nobody around for thousands of years. And yet the actual archaeological record shows a population explosion, essentially, because there's a lot more people in the Great Plains and Western U.S. making artifacts just after Clovis. It really looks like there's a lot more people on the landscape spreading out, leaving their artifacts behind. So there's just simply no evidence of some sort of population.
It almost gets bigger after Clovis. It doesn't. There's not a. It clearly does.
It changes significantly. The archaeological record changes significantly. There are a lot more sites after Clovis on the Great Plains and in the Western U.S. For sure.
You brought up another point I think we should talk about a little bit is the first people in Americas. In North America, I mean, this is an ongoing debate right now, and I want people on my show to talk about this because I've been emailing people that they're not responding. Are you aware? So I'm sure you're aware of the white sands footprints that are dated to 20 to 23,000 years ago using optically stimulated luminescence, OSL dating, along with radiocarbon and affecting supposedly for this dead water effect in this old lake bed. But there has been a new paper out. Have you seen this by David Rhodes? Like just in the last 2 months or just this year? Rhodey, sorry. And I don't know David, but he published a paper raising a lot of issues with the dating again. Oviatt, Jack Oviatt. He was at Kansas State. He wrote an initial.
You know Jack, yeah.
He wrote an initial response to the footprints saying these had dead carbon in the radiocarbon. And I don't want to get too much into the fines of that, but basically he made the issue that the dates could be too old because of addition of non-radioactive carbon. They came back with the OSL dates, and then now Rhodey has come back with another paper. I haven't gotten through it, but I emailed him because I wanted him to come on because I want to talk about these footprints. He's making the claim that they date till after the LGM. The dates now are like in the new paper between, if I remember, 17 to 14,000 years ago, which still make them old, pre-Clovis, if I'm right, if I think, but not pre-LGM. So that was the crazy thing about those white sands. 20 to 23,000 years ago puts them solidly in the last glacial maximum. Yeah. And that means, Alaska, there's no ice-free corridor, even though I know the ice-free corridor is kind of debunked, but that would have been still closed.
There has to be an ice-free corridor, right?
Yeah, they're eventually formed, but the idea that they came through that was the earliest migrations came through. You don't think?
It's not debunked. I mean, it was open 14,000.
Because I thought the coastal route is now the
coastal route is a topic.
But it's a hot topic.
But just the latest dating sort of synthesis of the ice sheet shows that the corridor was started opening by 14,000, ice-free corridor. Okay. The problem on the coast, of course, you've got sea level rise, you've got tectonics, and you've got glaciers. So it's very messy. But it's pretty clear that the ice was retreating from the coastal areas. As far as I'm concerned, I don't have a problem with either one. People want to make a either or debate, which is kind of silly. Look at the data, folks. They're both open, period.
Okay. Okay.
In neither place is there an archaeological record older than Clovis so far. In neither the ice-free corridor or along the coast.
Oh, I see.
So it's sort of a moot issue. We still don't. But so you have the archaeological record in the corridor, you have the archaeological record on the coast, you have the geologic record of the corridor and the geologic record of the coast. Those are 4 independent data sets. And so we know the corridor was open before Clovis. We know that there was pretty much ice-free and water-free. There was probably some exposed land along the coast. What we don't have in either place is an archaeological record that's older than Clovis. So it's still a mystery.
Interesting.
But to go back to white sands, my name's on the original paper.
You're on it.
I had started working there. So I'm not going to go into the details. I had started working there in 2012. And by coincidence, I actually was looking at some exposures, some trenches that were about 100 meters from where the tracks turned up. And I had some dates. Anyhow, now I know that Dave Rhodey and some co-authors had a paper sometime last year, I guess, a big paper. And then there was a rebuttal to that paper by the people involved in the dating with the U.S. Geological Survey.
Really? I did not see
that.
I
don't know about new dates. I don't know that anybody has new dates. I think part of the issue is that there are a lot of explanations for why the dates may be in error, but there are no new dates. What you've got you have the original dates, mostly radiocarbon on seeds. And then in the paper with the luminescence dates, there are radiocarbon. So the original paper is 2021, and then the OSL, and more importantly, to me anyway, their pollen dates, that was published in 2023. And the OSL and the pollen dates fit the original seed dates. So they're all internally consistent. And you have to explain that if you're going to explain problems, because pollen, and there's several layers with seeds. I think they dated 2 layers with pollen, and then 1 zone of the OSL. And so if there's a problem, you have to come up with a mechanism that affects all of the different kinds of dates in the same direction by serendipity, because the issues with pollen are very different from the issues with the dating of the seeds and the hard water effect, because pollen is going to be affected by the hard water effect. Yet the pollen dates are almost identical to the seed dates. So just make a long story short, then I don't have a problem with the radiocarbon dating there, or with the dating at all. Because one of the things that a lot of people don't pay attention to in the original paper, and I've been doing more work on this, is that those tracks are in stream deposits. Fresh water, it has to be fresh water coming off the mountains out into the lake. And the fresh water, I think, is the key there, because the fresh water, it's shallow water on a stream. And so it's going to have, the carbon will be in equilibrium with the atmosphere. And I think that takes care of the hard water issue, is those seeds weren't being affected by hard water because they were growing in a freshwater floodplain. By definition, the floodplain will be freshwater. In fact, the sediments with the tracks, they really stand out because they're red. And the only way you can get red sediment into that lake system, it's on the edge of a paleo lake, is off the flanks of the valley along the foothills of the mountains. And so that the only way you can get that from the source out onto this floodplain is by fresh water, either snow melt or rain or ice melt, for that matter, coming off the Sacramento Mountains. Okay. So I don't have a problem with the dating. I think it's solid. Well, there's another reason I don't have a problem.
What is it?
This gets a little in the weeds with radiocarbon dating, but the very first date I ever got when I started working out there, 2012. And again, this is about 100 meters from where the tracks, as just by absolute dumb luck. I collected a sample of mud. It's just black mud, lots of carbon in it. And I was going to date the carbon in the mud. And so my lab assistant was over in the lab, and she calls me and she says, "Hey, Vance, there's some seeds in here. Do you want me to date those?" I said, "Well, sure, date the seeds." And so what we ended up with, a date on seeds and date on 2 fractions of sediment. And they were identical, all 3 identical. And the isotopes showed that the sediment, the origin of the carbon in the sediments was very different from the seeds. If you could make an argument, oh, well, maybe it was just weathered seeds and they're all contaminated, but the seeds have a very different isotopic signature than the sediment, which tells me that the sediment has nothing to do with the seeds, and yet the dates are identical, essentially identical. And that's actually in the original paper, but it was in an appendix, and nobody has paid attention to the appendix. But anyway, I don't have a problem with dating.
You don't have the problem. So you're in the camp that it's still 20 to 23,000 years ago.
I don't see. Yeah, I've been doing a lot of research and on my own, trying to understand the bigger landscape setting of that site. And so
that's very interesting.
Another chat in a few months.
Yeah, that would be. I'd love to talk more about the dating.
Because I've got a paper in the mill, so we'll see how that plans.
Keep an eye out. I'll definitely keep an eye out, because I wanna know everything about these footprints. These are huge. If they're 20 to 23,000 years ago, it's during the LGM, way before Clovis. To me, the thing that's also amazing is they're in the interior of North America. We're not talking coastal. They're today is a desert, but back then clearly was a lot.
Yeah, it's a big lake.
Big lake and a lot more wet.
Yeah, no, it's bizarre. It's just no doubt.
It's so bizarre. That doesn't make any sense. And even if Rhodey, and I may be wrong with my quoting, says they're 17 to 14,000 years ago, to me, I was like, whoa, because that was like,
old. Yeah,
that's still old. And that's like the Meadowcroft rock shelter dates, which are debated, are like the ones they don't believe are like 17 to 14. And they say that's the coal effect. I've been to the Meadowcroft rock shelter in Pittsburgh because I did my PhD at University of Pittsburgh. Yeah. And they mentioned the coal problem. And I'm a radiocarbon person, so I went to the site and I was like, "Where's the coal?" in the rock shelter. It's a sandstone above it. There's no coal in the cave. There's coal in Western Pennsylvania. Yes, but that doesn't explain. To me, I was like, there's no coal. I was there. I was in the cave. I'm like, there isn't a coal layer in here. So what are they saying? It's coal contamination. And it would even go back. I would bring it up to people at Pitt, and they're like, oh, the texts that ran those dates, they don't believe those dates because of the coal contamination. Like, what is going on here? But people just say these things.
I know some geoarchaeologists who were on a field trip there many years ago, and they claim that they saw coal.
They saw coal in there.
For the cave, but
okay.
This debate will never be solved.
It'll never be solved. So yeah, but if you still have coal in there and you found like a stick or a piece of cultural organic matter, you would still think that it wouldn't necessarily affect that date.
Exactly.
Unless the coal was literally in the rope or the wood somehow.
Yeah, whatever. Yeah, no, that's a fair point. Yeah, my approach is you have to take each site on its own. No one site is going to solve the problems with any other site. But, when the original this debate, as you probably know, goes way back into the Middle Ages. And there were a bunch of American Paleolithic sites, so-called, reported, and they were debated and, debunked at the time. Well, when the Folsom discovery came along in 1927, sites didn't magically become good sites. No site proposed as Pleistocene turned out to be Pleistocene after the Folsom discovery, right? You get what I'm saying? So that the discovery of Folsom didn't change how we interpret any other sites. None of them turned out to be of Pleistocene age, the ones that were criticized. They were criticized for good reason. Folsom changed everything because you had an obvious artifact associated with Pleistocene bison. And that changed the game in North American archaeology. And so my point is, though, that didn't change the quality or the dating of any other site. And so even if you've got 23,000-year-old footprints at White Sands, it doesn't change any of the controversial sites. Each site has to be interpreted on the basis of its data. They have to stand on their own. And I've seen people make that argument. Oh, well, such and such a site, maybe it is, pick a number, 20,000 years old, because, White Sands is that old. Well, you've got to make the argument on the basis of the site. There are archaeological questions, and they have to be answered by archaeological data from the sites. So
I guess you can maybe make the argument it raised, to me, those dates from White Sands just raised the possibility of much older humans in the interior of North America.
Yeah, it does. It's exactly.
Now the possibilities out there in the world, like, holy crap, there could be a 20,000-year-old site in Tennessee. There could be one in Georgia. I mean, So not that it doesn't justify, like you said, but now all I would say is you got to now consider that humans are in Southeast North America at 23,000. That, to me, as geologist who studies paleoclimate, it still doesn't make sense to me. It doesn't make sense.
What I often think about is why, some people will argue then that, you've got human footprints 23,000 years old. Therefore people have been in the Americas ever since. If you add up all the proposed pre-Clovis sites and divide that into 10,000, so the track site, the oldest is 23, Clovis is 13, that's 10,000 years. And you take 10,000 years and divide that by the number of even the most far out plain pre-Clovis site, you still come up with 1, 2, 3 sites per 1,000 years. Where the hell is everybody? I personally, just based on the data at hand, which is how I deal with the world, the geological world and the archaeological world, to me that suggests you've got dribs and drabs of populations that get into the Americas, north and south, and they're around for a while, and then they're not. And then another group makes it up somewhere, and we find their sites, and they're around for a while, and then they're not. Because it isn't until Clovis, so you have continent, essentially coast to human occupation, just boom. Something's it's a weird story. Why don't we see a gradual increase in the number of sites through time? And you really don't see that. There are a few more in the 14s, I guess, 15s maybe, but you're still talking about like literally a handful. And then all of a sudden there's Clovis. To me, that's still the biggest mystery.
It's so weird. Maybe I'm thinking like, is it we're having a preservation issue? There just aren't many sites from that time period. Another thing is if maybe they're coastal populations in the LGM, and that a lot of these sites.
Yeah.
Yeah, because there's some work in Florida in those sinkholes in like shallow water off the coast that they're finding cultural remains. So, but yeah, you'd still think there'd be some terrestrial stuff left.
Because people should be living in the same places. They need water, they need food, they need shelter. Why aren't, and you think about all the construction work, it's been 50 years now since legislation's been passed, national and statewide, for, archaeological preservation, cultural resources. And there's been just tremendous amount of construction, but we have a lot more holes in the ground and a lot more archaeologists looking at those holes in the ground. Why aren't we turning up more old sites? And that's how I view it. I mean, other people have their own views, but that's my approach.
It makes sense. And you would think the only explanation, right, like you mentioned, is they must have been very small populations, very mobile. Maybe there were some bottlenecks, like they were, populations did decline for whatever reason to maybe a few, and just didn't make a big impact on the landscape enough to.
That's how I look at it. What's the record? How do you explain what we know now? That's my approach. I mean, other people have different ways of interpreting that. That's fine. We all have our ways. That's how I look at it. Mm-hmm. When you get back to that paper by Rhodey and others, if you find some specific new dates, let me know. But I don't think anybody has new dates, but I could be wrong.
Okay, it might have been recalibrating in like something like that.
They were trying an explanation. This is the other part of my view. Is so far we have dates from the USGS. Mm-hmm. All the papers that criticize those, and there's nothing wrong with that, but nobody has new dates. They have explanations for what might be happening. That's
understood.
All. Now, that's that's not bad. I mean, that's how science works, right? Is we debate these things and sort them out and set up testable hypotheses. So that's where we are.
Yeah, there's a difference between reinterpreting other people's dates and presenting new dates.
Exactly, yeah.
And new methodologies like OSL, radiocarbon, and, whatever else could be useful.
I mean, there are situations, I've seen a lot of them where, somebody proposes a new site of such and such age, and there might be some obvious stratigraphic problems, or is it an artifact? That's another thing, is that broken stone? Is that broken rock?
That's the 100,000-year-old paper. Yeah, that's the paper from California, right?
Well, there's more. That's the most.
That's the smashed rocks and stuff that they think is 120 or 120,000 year old. Which I've talked to several people and I've looked at the paper, and that is not. It's speculation more than anything evidence. Like they think it looks cultural, and like there's other things.
Exactly right. It might be, therefore it must be.
Yeah.
And if you get 130,000, and that's a minimum date. If you're going to get people in the Americas at 130,000, you're not only changing a paradigm for a peopling of the Americas, you're changing a paradigm for the peopling of Northeast Asia. That's got to be a slam dunk argument, not a, well, it might be archaeological, therefore it must be archaeological. That doesn't cut it. You've got to have
that's an interesting way to look at it too. If you say the dates are 130,000 years, 120 in California, you're changing the population, the Homo sapien population history of Asia.
You've got to have a better story then.
So you're way well along. You're down in like Neanderthal, like Julensis, and all those different Homo groups that were there.
A pile of broken bones and broken stones. They ain't gonna cut it.
Yeah. So okay. Anyway, we're at about an hour and 48 minutes. But to recap, I want to kind of close this up here. We, looked at the Younger Dryas. It's a climate reversal that happened 12,900 to 11,700 years ago. It is found in the Greenland ice record. It's found in the northern hemisphere, but it's not expressed around the world in any sort of consistent manner.
Not in terms of cooling.
Not in terms of cooling. You basically make the argument that there's no support that human populations diminish in any significant capacity at this boundary, that late Pleistocene megafauna were wiped out at this point. And you also take issue with like you just said, that this was a global climate event in general. And so you're more in favor that the Younger Dryas is driven by natural internal processes that are characteristic of most interglacials or other periods that were warm in recent Earth history.
Glacial interglacial transition.
Yes. And during those transitions, you see these rapid either warming or cooling, these what I call non-linearities. And if we invoke meteorites to explain the Younger Dryas one, then we have to explain meteorites to explain all of them. And there's tons of them. And clearly that's not the case. And other meteorite impacts we've seen around the world in recent history don't have a big impact. Especially if they don't leave a meteorite, a crater, it's going to be a blip on the radar of climate of Earth. And during our conversation, I'm now more of this favor that Earth's climate system, it's used to meteorite impacts. Now I think about it more, it's got to be. It's a natural... We've been being hit by bits of space rock since the beginning of 4.5 billion years ago. So, I mean, it doesn't seem like that even now is that anomalous to me anymore.
No, I think the extraterrestrial experts, astronomers, astrophysicists, and all would agree, or even people who study impacts would agree. One of the people on that paper, what his job was, how do we spot these things if they're on their way to Earth, and then what are the potential consequences of, all as a result of the Chicxulub thing has been. So he's spent a career involved with that.
And that's Mark Boslow, right?
Yeah.
He's a co-author on your paper.
Yeah.
So he's an expert in meteorite impacts.
Yep, he is.
And he's looked at this, and he's not convinced with the evidence of the Younger Dryas impact.
Yeah, he'd be an entertaining guest for you. I don't want to volunteer him, but
I'll keep him in mind. But to close this out, I want to say I'm looking forward to your new paper on these white sands footprints. And when it comes out, I'll be sure to read it. And maybe we'll have you.
It's in
What's
the
that? It's in the mill.
It's.
So is it in revisions or is it in review?
I just sent it out for review.
Okay. So yeah, there's some time.
There's still a ways to go. Yeah.
Okay. But I'll still keep an eye out for it. And if you see any of your co-authors that worked on the original paper on the 23 to 20,000 year old footprints, let them know that I'm interested in talking about it a little bit more on my show, because if you look around, podcasts and YouTube, there's a lot of interest in these footprints. And I think I've sent them a few emails. I said, I want you to come on and talk about your own paper. I don't know. Sometimes USGS is hesitant to have because they're government employees, to speak on behalf of government. That's where it's great for us to be independent academics. You're retired, but I'm a researcher, so I'm kind of like a free agent. I can do what I want.
Most universities like the PR just to be, at the most basic level. They want us out there because sharing our research, we're spending money. Somebody's supporting, what we do, we hope. Yeah. So we owe it to the public, particularly, a public research university. Yeah. We owe it to the public to let people know what we're up to. That's how I look at it. But the survey and all that, some of those scientific agencies, that's a whole other issue. Yeah, I would never speak for them. So.
I realized when I started this, and I was thinking about starting this channel, is science has a huge communication issue. we are writing these papers like we're Isaac Newton in like the 1500s, or like Albert Einstein publishing his relativity papers. And it like that format was put in place in the 20th century, papers and peer review. But the problem is no one reads those in the public. You can hardly get academics to read them anymore, and really to read them and sit through it and dig through the papers. So I was like, this is, I think, a big opportunity with YouTube and this open source kind of video making, that I can just, when I see an interesting study, I follow a lot of this research, I'm just going to email the authors on the paper and get them on to talk about it. We can link their paper. They get more press. And if there's a controversy around their paper, they get their chance to say it for the record. And hopefully we can build up these interviews. And then, they're out there in perpetuity now, so that people can actually go and see
that's a good idea.
The real scientists. There are always these faceless beings behind the paper. You see their names, but you don't know what they're like or who they are. So that's what I want to do with this channel, is get people like you, Vance, on here to get us to talk about all this crazy cool research. I love anthropology, archaeology, climate, and how they intersect. And so when you have your new paper, when or if, I'm going to say if, just to be safe,
I know,
it gets published, I would love to hear more about it and maybe bring you back on the show.
I'll let you know.
And I'll keep an eye out on my email for that. But anyway, do you have any final thoughts or shout outs you want to make? I'll definitely include your papers in the description so people can download or take a look.
Plan on never writing about the Younger Dryas again.
After the beast, I would not blame you. That paper, and then your response paper is, it's just like so absolutely massive and so many citations. And
well, that was
definitely don't blame you.
Group effort. Believe me, it was a group effort. Everybody committed. Everybody participated. All those names participated in a significant way, and most of us wrote a lot of the paper. Yeah. Anyway, I'm glad you're doing this. Good for you.
Okay. Yeah. Well, thank you. I appreciate I'm glad again for you to be on here, and
stay in touch.
And when I'll talk to you again.
Okay. Take care, David.